Hi, this is the seventh lesson in electricity. In my previous lesson, I discussed about voltmeter and the effect of internal resistance of voltmeter in readings. Okay, first in this lesson, I'm going to discuss about the internal resistance of the ammeter. Why should it be very small? Normally, we say internal resistance of ammeter should be very small. Okay, so for that, I'll consider a simple circuit to explain why should it have lower resistance, or theoretically why should it have resistance equal to 0. Always ammeter reads the current flowing through it. So if you want to measure the current flow through a component, the ammeter should be connected in series with that component. Then only, without splitting the current, the same current that is flowing through the component also will flow through the ammeter. So in this circuit, a simple circuit, the component which has resistance capital R is connected to a power supply. If you want to measure the current flow through this component, the same current should flow through the ammeter also. So ammeter must be connected in series with this component. So ammeter reads the current flowing through it. So I want to measure this current. This is the actual current flowing in this circuit, which is EMF over R. To measure that current, I connected an ammeter in series with that resistance. So the total resistance of the circuit will be equal to RA plus R. Now the current flow will not be the same as the actual current. It's going to change now I1. So I1 will be equal to EMF over total resistance, that is R plus RA. So the reading of the ammeter will be equal to EMF over R plus RA, which is lower than the actual current flow in the circuit. So if I want to have the reading which is equal to actual current flow, then RA must be equal to 0. That means we say ideal ammeter which has 0 resistance, that will read the actual current flow. Otherwise, it will read a value which is lower than, you can see here the denominator is R, here the denominator is R plus RA due to the internal resistance of the ammeter. So the reading of the ammeter will be lower than the actual current flow. So to have closer value, so if I want to have the reading very closer to actual current flow, RA must be lower. Okay, so RA must be lower. The interest of the ammeter should be much lower to have accurate reading. So next I consider about the internal resistance of a cell or internal resistance of a DC power supply or battery. You know, all the power supplies made of compound, some materials, if you think about a dry cell or just a car battery or whatever it has resistance due to its materials used in those cells or batteries. So due to the materials used, there will be resistance, and that is called the internal resistance of the DC power supply. So same current will flow through all parts of the battery or cell or the DC power supply. So we can imagine a real cell or real power supply as an ideal power supply. Ideal power supply means which has no internal resistance. So far in all my questions, examples, I considered an ideal power supply. I never talked about internal resistance of a cell or power supply so far. But practical power supplies, all the practical real power supplies have internal resistance. So we can imagine a real power supply like an ideal power supply which consists of internal resistance in series with it. We can show it by the following diagram. So I can imagine a real power supply like this. An ideal power supply, this one, is connected in series with its own internal resistance, which is denoted by symbol R. So imagine this is the dotted line indicates the real power supply. Imagine I just drew a dry cell. So you can imagine a dry cell like there is an ideal cell inside, it connected with its own internal resistance. Sometimes students have wrong idea. They think resistance is kept inside the cell. No, not like that. Actually, what I drew here as a resistor is the internal resistance of the cell due to the materials used up, right? So I can't separate the internal resistance or I can't remove the internal resistance from the battery or dry cell. It's inside that due to the material, right? So I can imagine a dry cell like there is an ideal cell connected in series with its internal resistance. So the same thing, the dotted line indicates the DC power supply. So the terminals used to connect the dry cell to the external component are these points. So the voltage applied across the external resistor or external component is the voltage across its terminals. I can name the terminals these X and Y. Same way I can name here X and Y. So the voltage across XY is applied across the external component. The voltage across the terminals of the cell is called terminal potential difference or terminal voltage of the cell, right? So here I can consider the total resistance. So now look at here. For the circuit, when I consider the circuit, the total resistance is capital R plus simple r, because you know there are no junctions or branches between the external component and the power supply. So the resistance of the external component capital R and the internal resistance of the cell, they are connected in series. So the total resistance of the circuit is given by R plus capital R. So the current flow is given by EMF over R plus symbol R. So symbol R is the internal resistance of the cell. So cross multiply IR plus IR equal to EMF. Now look at here. The voltage across the terminals of the cell is the voltage applied across the external component. So voltage across the cell is the voltage across the external component, that is I times capital R. IR is the voltage applied by the cell to the external component, and that will be the terminal potential difference. So IR I can denote by V, and that is the terminal potential difference of the cell or of the DC power supply. So I can say V plus, if I consider this equation, V plus IR equal to EMF. So V is equal to EMF minus IR. This is given in your data sheet for Excel Cambridge. It's given in your data cell. In case if they ask to derive this, you can derive that this way. Terminal potential difference is equal to EMF minus IR. So I into simple R is the voltage drop inside the cell due to its internal resistance. So remember that the terminal potential difference is always lower than the EMF of the power supply. Okay, so I can derive the same equation by considering conservation of energy, that is conservation of power. So I can say power generated by the power supply is equal to total power dissipation or total power loss in the circuit. So total power generated by the power supply equal to total power loss in the circuit, means the power is lost or dissipated in the internal resistance as well as the external resistance. So due to the power loss in the internal resistance of the cell, the power supply will get warmer. You would have noticed that when you are using your mobile phone, the battery of the mobile phone gets warmer. Or when you are using your laptop without main power supply, when you are using your laptop by using the battery of the laptop, you will see when you use it for a longer time, the battery gets warmer. Why it gets warmer? Due to the power wastage, power dissipation inside the power supply, inside the battery, which is I squared R. Due to that, heat is generated due to the internal resistance of the cell. So I'm going to get this equation. I'm going to derive this equation by using conservation of power now. Okay, so here I can say power generated by the cell is equal to power loss in the cell, that is due to the internal resistance of the cell, plus power loss in the external component capital R. So power generated by the cell is equal to EMF times I. Power loss in the cell is equal to I squared R. Power loss in the external component is equal to I squared capital R. So divide the whole equation by I. That will be equal to EMF equal IR plus IR. But we know IR is the voltage across the external component. That will be the same as the terminal potential difference. I denote by V. So EMF equal to IR plus V. Make the V subject. V is equal to EMF minus IR. So I got the same equation what I got here. Okay, so next I'm going to discuss about how to measure the internal resistance of a cell. So we can have a simple circuit like that. Real cell which has internal resistance symbol R is connected in a circuit like this. Ammeter, which is ideal ammeter, no resistance, has a ammeter has no resistance. A variable resistor, and this resistance almost like 20 ohms I can use for the protection of the battery, because in case if RV becomes 0, it will become short circuit. There will be high current flow that can damage the cell. So to protect the cell, resistance, low resistance, something like 20 ohms is connected. A voltmeter is connected across the terminals of the cell. So voltmeter will read the terminal potential difference of the cell. When RV is changed, when the resistance of the variable resistor is changed, the current flow will change in the circuit. You know, current flow is given by I equal EMF over RV plus R. So when RV is changed, current flow will change. When current flow changes, the terminal potential difference V equal E minus IR. So when I changes, terminal potential difference will change. So this is a very simple practical. I can finish it in 15-20 minutes. Like vary the value of RV, and for different values of voltmeter reading, record the relevant ammeter readings. Okay, by changing the RV, record voltmeter reading and the relevant ammeter reading. Voltmeter reads the terminal potential difference. Ammeter reads the current flow through the cell. Okay, so there I should put symbol capital R also. That is the resistance used for protection of the circuit. Okay, so I can say V equal E minus IR. So I can change the RV and get different current flow, different ammeter readings. So when ammeter reading changes, voltmeter reading also will change. I'm going to plot a graph of voltmeter reading against ammeter reading. So I should rearrange this equation. V equal minus Ri plus EMF. So this will be Y equal, this is the gradient, this is the x-axis, minus plus C. So plot a graph of voltmeter reading against ammeter reading. You will get a straight line. If I start the graph with 0, then the y-intercept point will be equal to EMF. Find the gradient. Gradient will be equal to internal resistance. So the gradient is going to be negative. Negative gradient is equal to minus R. So modulus of the gradient will be equal to internal resistance of the cell. And the y-intercept point will be equal to EMF if I start the graph from the x-axis of the graph from origin. So when I'm not using the precautions here, I can put a switch here somewhere, right? Why should I put switch here? Because when I'm not using it, the switch should be off, or I should open the switch, because if the current flows continuously, the EMF will run out and I won't get a straight line graph. So whenever readings are taken, during that time, switch on the circuit, otherwise switch off it. So otherwise, if you keep the switch on, the EMF of the battery or the DC power supply might decrease continuously, then you won't get a straight line. So that is one of the important precautions in this experiment. Okay, so next I'm going to consider the condition for getting optimum power in the external component. You know, when we consider a DC power supply, a real DC power supply that has internal resistance. So the optimum power, the power output or power supply to the external component depends on the resistance of the external component. So what is the condition to get optimum power? I'm going to discuss now. For that, I'm going to use a simple circuit again. Okay, so here the current is given by I equal EMF over R plus R. So power supplied to the external circuit is given by E equal I squared capital R. That is going to be EMF squared over R plus R all things squared into R. So you can see that when R varies, the power is going to vary. Okay, mathematically, you can say when R is equal to 0, the power will be equal to 0. That means when the external component has no resistance, anyway, practically there is no component with 0 resistance. If I short circuit or whatever it is, when R is equal to 0, the power transfer to that one will be equal to 0. Right? Same way, when the external component has very large resistance, so theoretically we say when the resistance of the external component becomes theoretically infinity, what will be the power output? Okay, little bit of mathematics there. I'll write like this. Okay, so divide numerator and denominator by r square. Don't worry about this mathematics, just I quickly do, but mainly I'm going to consider the practical part next. But just I want to show the pattern, how the power varies with r. So divide numerator and denominator by r squared. When I divide it, it will become EMF squared over r. Okay, so when I divide the denominator by r squared, it's going to be 1 plus r over r all things squared. Anyway, don't worry about the mathematical part, simple algebra. I divide numerator and denominator by r squared. So when I divide this by r squared, e squared over r, because one r will get cancelled here. Then when I divide the denominator by r squared, when I take the r squared into the bracket which consists of square, it will become r over r, so 1 plus r over r all things square. Now you can say when r becomes infinity, what will happen to the power? When r becomes infinity, the numerator will become 0. When you divide any number by infinity, it will become 0. So that becomes, power will become 0 over 1 plus, again this will be 0 all things squared. So that will become 0. See, when the r equals 0 also, power is equal to 0. Right? When the resistance of the external component is equal to 0, that also gives power 0. When the resistance of the external component becomes very large, theoretically infinity, that also gives 0. So that shows it's going to be a curve. There will be an optimum power. Right? So I can do that mathematically by using differentiating it, but I don't want to go to that mathematical part, not in your syllabus. So we will do a practical, right? Practically we can find the condition to get optimum power. So I'm going to draw the circuit diagram for getting the optimum power. Okay, so experimentally I'm going to get the condition. So for that I made a circuit, I'll complete a circuit. So a real power supply is connected to a variable resistor. Ammeter records the current flow through the variable resistor. In this circuit, I consider both the voltmeter and ammeter ideal. So you know the meaning of it. No current flow through the voltmeter. Resistance of the ammeter is 0. So here the voltmeter records the voltage across the RV, the variable resistor, the voltage across the variable resistor. Ammeter records the current flow through the variable resistor. So if I multiply the voltmeter reading by ammeter reading, that will give the power transferred or power dissipated in the external component RV, voltmeter reading into ammeter reading. Same way, because I'm using a rheostat, so in rheostat I can't find the resistance, so I need to record the resistance. So I can find the resistance of the variable resistor, or I can say I can find the resistance of the external component in the circuit by dividing the voltmeter reading by ammeter reading, R equal V over I. Okay, so what I'm going to do in this experiment, I am going to change the value of RV, maybe 10 readings I'm going to take. So change the value of RV for each position of the variable resistor, you know, the rheostat. I'll record the relevant voltmeter reading and ammeter reading. So for each readings, calculate the resistance of the variable resistor by dividing voltmeter reading by the ammeter reading, and calculate the power transfer to the external component. Here Again, variable resistor is the external component that is given by voltmeter reading into ammeter reading. So I am going to plot a graph of power transfer to the external component against the resistance of the variable resistor. So when you plot a graph, you will get a graph this shape. So this is the power output and this is the RV. So if I start the x-axis from origin 0, you will get a graph like this shape. It will come asymptote and there will be optimum power for a particular value of RV. So from the graph, find the value of RV that gives the optimum power, the maximum power to the external component for the given power supply, which has constant EMF, constant internal resistance. For that, optimum power is transferred to the external component. So you will see that value will be equal to, interesting, that value will be equal to internal resistance of the power supply. That means when the resistance of the external component becomes equal to internal resistance of the power supply, optimum power will be transferred to the external component. Okay, but there's a wrong concept or wrong idea. Students thinks optimum power transfer to the external component does not mean maximum efficiency. That also I can do mathematically, but I don't want to go in detail mathematics. But should remember that I can get optimum power in the external circuit when the resistance of the external component becomes equal to internal resistance of the cell. That means when R equal R, optimum power will be transferred to the external component. But remember that that does not mean the maximum efficiency of the power supply. No, that is not true. The maximum efficiency of the power supply, I can show mathematically. Maximum efficiency, that is 100%, will be obtained when the resistance of the external component becomes infinity, right? But anyway, I don't want to go in mathematical detail, but I'm going to discuss a question now. There, I will consider the resistance of the external component lower than the resistance of the internal resistance of the cell. Then what will be the efficiency? When the resistance of the external component is equal to internal resistance of the cell, what will be the efficiency? There the optimum power will be transferred. Then when the resistance of the external component is larger than the resistance of the internal resistance of the cell, what will be the efficiency? Okay, so from that you can find out optimum power transfer does not mean maximum efficiency. Okay, I'll do that question now. Okay, so I made a question like this. DC power supply that has internal resistance 4 ohm and EMF 16 volt. There's a variable resistor. So we are going to find the power transfer to the external component. So here the variable resistor is the external component and the efficiency of the cell when the value of RV is kept at 2 ohms, 4 ohms and 10 ohms separately. So the same procedure for all three parts. So first I can say when RV equal to 2 ohms. So to find the power transfer to the cell, I need to find the current flow. So I know how to find the current flow. I is equal to EMF over total resistance. So EMF 16 over total resistance 2 plus 4, that is 6. So find the current flow when the RV is equal to 2 ohms. Okay, so power transfer to the external circuit we equal I squared RV. So that will be 2.667 squared into RV is 2. So that will be 14.226 watts. I'll give it in 3 decimal points. 14.226 watts or 4 point, yeah, anyway, it's okay, doesn't matter. So power, that is the power output. So I need to find the efficiency, right? Efficiency. I use blacking for that. Efficiency I can find when this one. So power generated I need to find. That is equal to EMF times I. So EMF is 16 times current flow is 2.667. So that will be 42.672 watts. So efficiency I need to find 14.226 over 42.672. So that will be 33.7%. So that means when the resistance of the external component is lower than internal resistance, that is 33.7%. Okay, second part I'll do shortly. So when RV equal 4 ohms, we know that gives the optimum power output. So I need to find the current flow, that is going to 16 over total resistance 4 plus 4, that is 8, that is going to be 2 ampere. So power given to the external circuit will be I squared RV. So that will be 2 squared into RV is 4. So that is 16 watts. That is 16 watts. So you can see that when the internal resistance is lower than the when the external resistance is lower than the internal resistance, that is 14.22 watts. Here this is 16 watts. You know that is more than this one. Right. So now we need to find the efficiency. So power generated we need to find. That will be equal to EMF times I. So that is EMF is 16 into I is 2. That is 32 watts. Efficiency 16 over 32 into 100. So that will be 50%. It was 33.7%. Now it's 50% increasing. We'll see what will happen when the external resistance is 10 ohms, which is larger than internal resistance. So that is the third part, right? So I'll raise this part. So we have written that we know the question. So I'll raise this part. So R equal 10 ohms. What will happen? That is the third part. 10 ohms, current will be EMF over total resistance 10 plus 4. So that will be 16 over 14. So current flow will be 1.143 amperes. So power transfer to the external circuit will be I squared RV. So that will be 1.143 squared into RV, that is 10 ohms. So that will be 13.064 watts. So I need to find the power generated. I need to find the power generated when the external resistance is 10 ohms. Equal to EMF is 16 into current flow 1.143. That will be 18.2288 watts. So efficiency, external component 13.064 over 18.228288 into 100%. So that is going to be 71%, 71.4%. See, look at here now. Now you can see that power transfer to the external circuit 13.064 here. Here 14.226, here 16. So you can see that optimum power, if you want, you can try different values, like more than 4 ohms to the external resistance, less than 4 ohms to the RV. You will see the maximum power will be transferred, that is in this condition when the EMF is 16 volt and the internal resistance 4 ohms is 16 watts. There we are getting the optimum power output when the RV is equal to internal resistance 4 ohms. But you can see the efficiency 50% only. During that time, the efficiency is 50% only. But when the external resistance becomes more than the internal resistance, the power transfer is getting lower, 13.064 compared to 16. But the efficiency is 71%. Check that. I think it's correct. Yeah, that is 71%. Yeah, that's right. So that is 71%. So now you can see the efficiency is higher, but the power transfer to the external component is not optimum. So understand that optimum power is nothing related to maximum efficiency. Okay, so I hope you understood these examples. In my next lesson, I will discuss a few exam style questions. Bye.